Hello and welcome to this IChemE Global Awards 2021 webinar. My name is Matt Stalker and I am your host for today's presentations. The IChemE Global Awards celebrate chemical, process and biochemical engineering excellence and are widely considered as the world's most prestigious chemical engineering awards. Today we'll be revealing the winner of the IChemE Research Project Award, sponsored by the Chemical Engineer. This award recognises the best chemical engineering research project undertaken in the last 3 years. Our awards judging panel has been hard at work in recent weeks to review and rank all of the entries, and here are our finalists. We have a joint entry from the Abu Dhabi National Oil Company and MicroSilicon, Bitrez, Johnson Matthey, a joint entry from North Carolina State University and Photocide Protection, and finally University College London. We'll be finding out more about 4 of our finalists in today's webinar, and you can ask your questions throughout the session. Simply use the questions box on screen and we'll put as many of the questions to the finalists as time permits. So let's get started with our first presentation, representing the joint entry from the Abu Dhabi National Oil Company and MicroSilicon. Please welcome Dalia Salim Abdullah.
That's great if you just pop that into slideshow mode. Brilliant.
Okay, excellent. Good morning, good afternoon, and good evening to everybody who has joined us from across the globe to this special event. So I'm really happy and glad to be here on behalf of my colleagues in ADNOC and our partners in MicroSilicon to present to you on the real-time monitoring of asphaltene deposition. My name is Dalia Abdullah and I'm the technology manager in ADNOC Onshore. Allow me to start by giving you a brief introduction into what asphaltenes are and what are the challenges that are posed by asphaltenes. So asphaltenes are known to be the heaviest component of the crude oil, and they're termed to be the cholesterol of the oil industry. As long as asphaltenes are soluble in the crude oil, there's absolutely no issues. However, under certain conditions or changes in conditions, I have to say, of temperature, pressure, or fluid composition, the asphaltenes will become unstable and they'll precipitate and then deposit. They can deposit on the walls of tubulars in our wells, or they can deposit in our flow lines or in our separators, and they can create blockages, and that can lead to loss of production. We can also have some safety concerns, of course, when asphaltenes deposit on safety valves and prevent them from functioning. We spend millions of dollars every year to try and resolve the asphaltene problems, to send in pumping units to our well sites, and to use solvents to clean up those wells and mechanical equipment to remove these asphaltenes. And with this high intensive operations, this leads to an increase in emission. Now, the asphaltene challenge, it's costing the energy or the oil industry globally billions of dollars. And we expect this problem to aggravate and increase in the future because we're going towards more complex reservoirs. We're going towards enhanced oil recovery using hydrocarbon gas or CO2 that we inject into our reservoirs. And these gases are known to destabilize the asphaltene. Now, one specific issue that we want to focus on with the theme of this presentation is that when asphaltene deposition happens, it happens all of a sudden. There's no early indications that we could follow. And it's often too late when we find out, for example, that some of our wells are down, completely blocked with asphaltenes. And to find out if asphaltene is building up in a well, we have to send in monitoring or units to the well site and do intrusive methods of going in with certain tools like calipers to see whether we have blockage in this well or not. So that was the motivation really behind this work. And that is, we want to find a real-time or develop a real-time asphaltene sensor that can give us an early indication of asphaltene buildups in our wells. And that's why ADNOC have invested in a research project with Rice University to look into a sensor that can be based on electron paramagnetic resonance, EPR, to look for a specific signal for asphaltenes to be able to detect that. Now, I just want to take you a little bit through the history of this project, that it started with a proof of concept in the lab in 2014. But then when we started the fabrication of the device, MicroSilicon came into the picture and they fabricated the device. That was in 2016. We brought it to our fields to do offline measurements in 2018. And then we were ready last year, brought in these sensors, and we have 2 of those in our fields hooked up to our facilities and monitoring and reading the fluid behavior for asphaltene deposition. Now, let me tell you a little bit about our sensor and how it works. It's based on the concept that asphaltenes have free radicals, and these radicals can resonate by applying strong magnetic fields. And so it has a unique signature, and we could measure the height of the peak, and that's proportional to the concentration of asphaltene in our fluid. So how could we use it? Basically, if we have the sensor reading the fluids coming from our wells, and we're getting a stable signal, it's telling me, okay, the asphaltene concentration is steady, so there's no issue. However, when this signal starts to change, for example, starts to drop, it's indicating that the asphaltene concentration in my fluid is dropping. So I'm losing part of that asphaltene somewhere along the system, probably in my well. And that gives us the early indication that we're looking for. But of course, before we go in to fabricate the device, we had to do a lot of measurements or verifications in the lab to ensure that this, using EPR, electroparamagnetic resonance, is equivalent, when we measure the concentration of asphaltene, is equivalent to our standard methods that we use in the lab, you know, the wet chemistry methods. And we did look at 100 samples from across the world from different oils, and this is correlated. We also wanted to see if the sensor has a limitation. Can it measure very low asphaltene concentration and very high asphaltene concentration? Can it look at the range, or is there a cutoff point? And we happily found out that even at concentrations as low as 0.1% asphaltene, we can still have a clear signal, and it's a reproducible result. So you could see from the graph below that we have asphaltenes from different wells and with different concentrations, and we could still see the signal, and it is reproducible. Now to the exciting bit, which is, okay, we have it ready. It's been, you know, proved in a lab in a contained environment. We brought it to the field, but we collected samples offline. But now we want to do this in real time. To do it in real time and to hook it up to our wells, the sensor can't go on its own. So it has to be fabricated in a device. So you could see the picture of that on the screen. There is a small separator, because of course we're measuring the asphaltene concentration. It's a component of the crude oil. However, when we produce from our wells, we have multi-phase production. We have gas, we have oil, we have water. So before, when we take a side stream to do the measurement, we have to have just the oil, and that's the function of that small separator that you see on the picture. And we also have a transmitter. So the sensor is collecting all this data. What do we do with this data? This is now the transmitter connects to a cloud architecture. And so we can get the data in real time. We have real-time access to it. And we have a program that gives us a visualization of what's happening with our fluid. And so the mode of operation that we're looking at is that the sensor is doing the measurement. It's providing us with the data. We're learning from this data, and we're doing control mechanisms. So we go for a mitigation, we take action, and that's where the benefits are of this device. Now, I'm showing you here just a snapshot of what we see in that platform. There are several measurements, by the way. This device does not only measure the asphaltene concentration, but you could see also in blue, it looks at the pressure measurement. We have also some impedance measurements. And it's really the combination of all this data together gives us the condition of our fluid and if there are changes in our fluid that we need to know about. And with that, I'd like to say that the principle of electron paramagnetic resonance for real-time monitoring of asphaltene deposition is now a reality. There's nothing in the market that looks at the asphaltene concentration or specifically measures asphaltene. So we're very excited about this. And it's just a message to people in the industry to invest in ideas like that, to go in with partnerships, either with universities or startups, in order to get something which is new and that can add value to the industry. We currently have, as I mentioned, 2 sensors in ADNOC that are currently doing the real-time measurement, and we have potential savings of millions of dollars annually and thousands of barrels in enhanced production due to lower downtime. I want as well to mention that the research component is not necessarily or does not necessarily stop in the lab. So even when we took the device to the field, there's lots of learnings and lots of things to improve. So one of the things that we wanted to focus on right now with MicroSilicon is to have maybe a self-cleaning mechanism for this device to reduce the maintenance, having to send somebody to the device to do some cleanup every so often. And then, of course, we're discussing commercialization plans to have this device available to other operators across the globe. With the relentless effort of ADNOC to focus on 100% HSE, there is, of course, a much more benefit to this device than just the early indication. We have reduced intervention, so we have something that's doing the measurements for us without having to send people to the location. So we're reducing interventions, reducing people's exposure to danger. We are reducing emissions because of, again, less operations required. We reduce chemical consumption, so we can have this device as well when we're doing chemical injections, continuous chemical injections to inhibit asphaltenes, which this is giving us an indication whether the inhibitor works or does not work. I need to increase the dose rate or decrease it. And of course, overall, reduce integrity risk. And with that, this brings me to the end of the presentation, and I'd like to take this opportunity to thank everybody who's worked on this and make it happen, from ADNOC side, from MicroSilicon, from Rice University, from Sogan, the local sponsor of MicroSilicon. And I'd like to thank as well the IChemE panel for selecting this project, and thank you for your attention.
Okay, thank you very much, Dalia. It's now time for questions, so we'll take a pause, and if you'd like to get in touch, please do so through the questions box. And whilst I give you a moment on that, don't forget there are more IChemE Award webinars coming up next week. You can find out all the dates and times by visiting the IChemE website. That's icheme.org/global awards. Okay, we don't have any questions, so we're going to move on. Thank you very much, Dalia. We will go on to our second finalist from Bitrez. We have a pre-recorded video, and then Paul Jones from Bitrez will join us live to answer any questions you have after this.
Today I'd like to talk about a new generation of ketamine epoxy hardeners. They offer long pot life, reduced hazard, and are technically enhanced ketamine curing agents for epoxy. Epoxy resins are employed in a myriad of applications, serving countless market needs. Formulated as single component high latency systems for elevated temperature cure, or as multi-part systems offering a broad range of processing options, the versatility of this resin chemistry is unprecedented. Whilst homopolymerization may be employed as a means of transforming the epoxy functional material into a cured state, Cross-linking with a co-reactant is more common. Co-reactants may include, amongst others, phenolic, amino or anhydrides, but amine and amine derivatives form the largest generic group applied to this end. So what kind of amine-derived cross-linking agents are employed? These amines are modified in many ways to convey improvements to technical, regulatory and commercial performance. Modification techniques include the formation of adducts, amidoamines and polyamides, mannich bases, association salts and ketamines. So what are ketamines? Ketamines are formed through the dehydration of a primary amine group with a ketone as depicted. The resultant ketamine that's formed shows stability if prevented from exposure to atmospheric moisture, but as the reaction is reversible, when combined with the epoxy component and applied, the ketamine is hydrolyzed, liberating the functional amine and ketone components. The regenerated ketone is a volatile, released from the film, and the original amine has active hydrogen groups that can react with the epoxy component in a conventional manner. So what makes them differ from other modification techniques? Ketamine curing agents are relatively unique insofar as they have a non-linear reactivity profile, providing excellent pot life whilst fast thin film cure. Historically, the ketamine curing agents derived from short-chain ethylene amines have offered the desirable reactivity profiles, but the liberated amines are generally of a low molecular weight with high vapor pressure with ensuing safety concerns. REACH regulations have also hindered or eliminated the use of these grades in Europe. So if they're being removed from the market, what is the solution? A new range of ketamines have been developed and they offer desirable pot life reactivity characteristics as associated with this class of curing agent, but they liberate amines of a much lower hazard classification. The new series of ketamine curing agents have been designed first and foremost for regulatory compliance. Consideration has been given to residual free monomer levels to reduce the hazard rating during application and to reduce some of the problems associated with free amine. Through design, the new ketamine epoxy curing agent series function through reaction with atmospheric humidity, but they are less prone to the problems associated with humidity during cure. Conventional ketamines, when hydrolyzing, liberate ethylene amines that are prone to compatibility issues with conventional epoxy resins. This can lead to surface migration or exudation of free amine to the coating surface. So what is the technical issue with surface migration? Surface migration of amines can cause, at best, reduced gloss or in some cases tacky or greasy surfaces, which in turn result in amine blush or amine bloom. These two phenomena are well documented, but essentially consist of moisture condensing or water-soluble compounds migrating to the surface of the coating. The moisture can react with CO2 and subsequently form ammonium carbamate byproducts. Aside from the negative impact that this has on the aesthetic appearance of the film, these side reactions can alter the formulated stoichiometry, resulting in an imbalance of the desired reaction. This in turn potentially reducing the mechanical properties and chemical resistance. So what about the new grades? The new series of ketamine grades offer enhanced epoxy compatibility. Some grades have additionally been modified for enhanced thin film cure to further protect against the aforementioned problems. So how do they compare? For comparative purposes, we will use the ketamine that has been commercially available from several sources and derived from diethylene triamine. We will reference this product as K1. This ketamine, along with a few variants, have been the conventional ketamines employed in formulated epoxy systems. The new and novel ketamines have been formulated to satisfy the REACH regulations and provide enhanced performance, obviating the less attractive aspects of the conventional grades. Regulatory considerations include the registration requirements of the conventional ketamine and the hazard classification. As detailed, the ketamine grades reverse in the presence of atmospheric moisture, liberating the amine. In the case of the conventional ketamine, K1, in its supply form, it has a free monomeric beta level of around 2 to 5%, subject to the supplier specification, the process employed, and the subsequent storage conditions. With exposure to moisture, the reaction liberates further DTA for reaction purposes. The ketamine reversal reaction liberates approximately 35% of monomeric DTA. One version of the new ketamine epoxy curing agent has been formulated so the initial free amine level is less than 0.2% as supplied. And following the ketamine reversal reaction, it liberates still less than 2% of monomeric amine as analysed on hydrolyzed product. This reversal reaction means consumers and formulators may be left with a technical and moral dilemma regarding label requirements, advisory information, as clearly the product supply label for conventional ketamine is based on the free amine as supplied. However, knowing that on application the product hazard increases, albeit only until such time as cross-linking occurs, then this may warrant some explanatory discussions with applicators who may become exposed to product listed as potentially fatal on inhalation. The new ketamine grade curing agents have low supply free amine levels and low free amines following hydration, so they remain consistent in terms of the hazard associated with the corrosive amine. Of course, in either case, the product liberates the solvent as a volatile component. Following the introduction of GHS, the threshold limits and reporting requirements for free monomer levels has been adjusted and the escalating hazard rating for free DTA is as shown. Obviously, health and safety is paramount, but what about technical performance? From a technical perspective, the new ketamine grades offer significant improvements in performance while still maintaining the desirable reactivity characteristics. Again, for illustrative purposes, the relative reactivity of small mass cure and thin film cure rates are shown, using the former conventional ketamine K1 as the benchmark value against one of the new generation grades. So this illustrates that the new curing agents offer significant improvement of working time and pot life whilst maintaining desirable high thin film reactivity. Alteration and extension to pot life is the main design driver for this generic product group, and the new ketamines satisfy that particular aspect as expected. Whilst they work just as well in this respect, and in addition to the aforementioned regulatory improvements, it is the technical performance during and after cure that sets them further apart from their analogous predecessors. It's evident that poor compatibility, exudation and surface migration of free amine can result in blushing and blooming issues, which offer aesthetic concerns, but the cosmetic defect is more an illustration of the fact that the intended or desired reaction hasn't fully occurred. These problems can also influence overcoatability and subsequent intercoat adhesion, which in turn can alter mechanical properties and chemical resistance. The new ketamine grades offer enhanced compatibility and they vary in terms of their surface appearance, with a moderate improvement to the surface film to a significant advance based on selected grades from within the range. The new ketamine grades are offered in several supply forms, with some high solids grades diluted with ketone and/or aromatic solvents or supplied free from any supplementary solvent, i.e. they're supplied with solvent free but acknowledging that the solvent is inherently generated following hydration. The stoichiometry differs from some of the original ketamine grades, as do some of the viscosity values, but the resultant mixed viscosity tends to be somewhat similar. Increased active hydrogen equivalent weights, although blocked, calls for increased curing agent addition. This in turn generally results in reduced viscosity of the mixed system. These grades can be used as curing agents in their own right, or they can be combined with other grades in order to formulate systems with bespoke reactivity and offer other process or cured performance attributes. In summary, we've developed a new series of ketamines. These products are REACH compliant, far superior to their predecessors, and they have reduced hazard rating. Thank you.
Okay, then that was a pre-recorded presentation from Bitrez, but we do have Paul Jones with us, so we'll once again pause, and if you have a question you'd like to put to Paul, please type it into the questions box now. Okay, we don't appear to have any questions, Paul, so thank you very much for being with us and thank you for that presentation. We will move on to our third finalist of the day. It's Johnson Matthey. Please welcome Norman MacLeod.
Good afternoon, everyone. My name is Norman MacLeod, and I'm a Research and Development Manager for Johnson Matthey, based in Birmingham in the UK. And I'm going to talk today about our work to implement a new highly stable methanol synthesis catalyst, Catalco 51102. Now, some of this presentation is a repeat from yesterday's innovative product event, so apologies to anyone who is seeing this for a second time. However, today I will include a bit more detail about the R&D phase of the project. First, a few words about Johnson Matthey. Our vision is for a world that's cleaner and healthier both today and for future generations. We use our cutting-edge science, working in close collaboration with our customers to make a real difference to the world around us. IChemE is a science and technology company with expertise across many fields, several of which were employed in the development of 51102. So competencies such as catalysis and advanced materials, product formulation and scale-up, characterization and modeling, through to process optimization. The successful delivery of this project involved a multifunctional team of chemists, engineers, and commercial colleagues, all working closely together over several years. Methanol is a major commodity chemical with somewhere in the region of 100 million metric tons being produced annually. It is used to make a wide variety of derivative chemicals and associated downstream products. And it's also increasingly being used as a fuel, either as methanol itself or as a blend. And currently, approximately a third of all global methanol production is ultimately intended for fuel duties. One particular area of interest in this regard is the potential to use methanol as a substitute for marine diesel. There is also significant interest in the future use of methanol as a hydrogen carrier and as a source of green fuels and chemicals via sustainably sourced hydrogen and CO2, which I'll come back to later. Now, to provide a little more context for this development, it's worth discussing briefly the history of the low pressure methanol process, which is the mainstay of the methanol industry. And that was developed on our site in Birmingham in the mid-1960s, employing the first commercialized copper zinc alumina methanol synthesis catalyst, 511. And the first plant using this catalyst had a capacity in the region of 400 tons per day. Since that time, there have been improvements in both catalyst performance and process design, such that world-scale plants now commonly exceed capacities of 5,000 tons per day. Now, since the 1960s, IChemE have introduced a sequence of ever more active and physically robust catalysts, and we are now on our 15th iteration. However, the single biggest improvement that we've made to the performance of the catalyst over those 50 or so years is that which is associated with the development of 51102. And this highlights that even with mature technology areas such as this, it is still possible to make step-out improvements. So how was this achieved? In the past, the focus has tended to be on improving the initial activity of the catalyst and then assume that any activity advantage that's obtained will be subsequently retained over the useful operating life of the charge. However, as you can see in this indicative activity versus time plot, methanol synthesis catalysts tend to lose a large proportion of their activity with time online. So with 51102, we decided to take a different approach. And so instead of looking to try and improve the initial activity, we targeted improving the long-term stability of the catalyst. Now, this change in focus created an immediate challenge for the research project, in that whilst it is relatively easy to measure the initial activity of a catalyst, it is much more difficult to evaluate over a reasonable time frame what the aged activity is likely to be under any given set of operating conditions. So to get over this problem, we had to design and build an accelerated aging microreactor system, and also develop aging protocols that would allow us to condense the equivalent of many months or even years of deactivation under plant conditions into just a few weeks of rig time. And once we had this system in place, this allowed us to evaluate the aged activity of different formulations in a very short period of time. And also by operating under a range of conditions, we were also able to use this system to generate data to help us to optimize our deactivation models. Now, having used the accelerated aging microreactor to identify interesting candidate formulations, the next important step towards commercialization was to validate the performance of the formulations under real-world conditions. And to do this, we used a pilot-scale side stream unit placed at one of our customers' sites. And we are extremely grateful to Proman USA and their Pampa facility for hosting and operating this unit. So having subsequently successfully validated the performance of the new formulation that became 51102 on the side stream unit, we then looked for opportunities to place commercial scale charges of catalyst with customers. And again, the first opportunity that arose for us was with Proman again, and also at the Pampa site. And this figure shows the performance of the first commercial charge of 51102 installed, which has now been online for over 2 years. Here, the activity of 51102 is plotted relative to that of the previous charge of catalyst that was installed at the same facility. And that previous charge was, again, Johnson Matthey material. It was the best of our prior generation catalysts. Now, both catalysts deactivate with time, but because 51102 is more stable and therefore deactivates less, there is a relative activity benefit that accrues over time. And as illustrated in this figure, this reached a factor of about 1.6 after about 2 years online. And we expect this activity advantage to continue to increase with further time on stream. And clearly this represents a huge improvement in the performance of the catalyst versus prior generation materials. Another exciting prospect for this development is in the area of green fuels and chemicals production via CO2 hydrogenation. And having a stable catalyst is potentially even more important in this duty due to the high partial pressure of water produced as a byproduct, which tends to accelerate deactivation. And we have found in our lab tests that variants of this development perform significantly better in these duties than prior generation catalysts. So to summarize some of the advantages of the new development, it can increase productivity on existing plants by maintaining high conversion over time. And on an example 3,000 ton per day plant, the cumulative extra methanol produced could generate additional revenues of up to $50 million over 4 years. The new catalyst can provide a significant improvement in operating life, perhaps up to double that of existing catalysts. And it also provides opportunities for further process optimization via new plant designs. And finally, the availability of highly stable formulations should facilitate development of green routes to fuels and chemicals via CO2 hydrogenation, delivering on JM's vision for a cleaner and healthier world. Okay, thank you for your attention, and I'll be happy to try and answer any questions.
Okay, thank you very much, Norman. So once again, we'll take a brief pause for questions. If you'd like to get in touch, please do so through the questions box. Okay, once again, we haven't got any questions, so thank you very much, Norman. We have reached our last presentation of the day. It is the joint entry from North Carolina State University and Photoside Protection. Please welcome Reza A. Giladi.
Hi, Reza. We can see your presenter mode with the next slide on it. Are you able to just swap presenter view and slideshow? Fantastic, thank you.
How's that? Perfect. Well, good afternoon, everyone. My name is Reza Giladi, and what I would like to begin first by acknowledging that as part of this presentation, I would like to say good afternoon to our friends, colleagues in the UK, in Europe, and in Africa. Good morning to those of us here in the Americas, and good evening to those joining us worldwide in Asia, Australia, and the Pacific. On behalf of my colleagues, Rich Spontak, Frank Scholl, my name is Reza Giladi. I'm the Chief Technology Officer of Photoside Protection, and it's a pleasure to tell you a little bit about our work on universal photodynamic coatings for infection control that we're presenting today as a research project finalist for the IChemE Global Awards 2021. A little bit about our company. Photoside Protection and NC State University are developing the Safe Light product line. This is the next generation family of environmentally friendly products in the terms of fibers, coatings, and other materials that can inactivate a wide range of pathogens, including drug-resistant and drug-susceptible bacteria, fungi, and viruses from surfaces to reduce their transmission to new hosts and to reduce diseases caused by surface transmission of pathogens. Our beachhead markets will be hospitals, healthcare facilities, and PPE manufacturers. As a company, we've been very nicely supported by the National Science Foundation, by the US military, North Carolina Biotechnology Center, and we've had a patent on this technology recently awarded so that we can go ahead and proceed towards manufacturing of our materials. So there's an unmet need for antimicrobial materials in the market space. Hospitals, nursing homes, daycares, and gyms are all examples of locations where pathogens can be transmitted from surfaces to new hosts, causing diseases. As a primary example, in the US alone, there are 1.7 million hospital-acquired infections, resulting in 100,000 deaths each year, costing about $30 to $45 billion. If we expand from hospitals to all healthcare facilities like nursing homes all across the world, we're talking about a problem that affects millions of people each year, resulting not in billions, not in tens of billions, but hundreds of billions of dollars in lost productivity and hundreds of thousands, if not millions, of deaths. In addition to the typical pathogens that are encountered in these environments, There are superbugs that arise from the overuse of antibiotics in traditional consumer products such as triclosan. Other serious threats for consumers that are foodborne include prepackaged food industry products or the food service industry. Of course, fungi, mold, and mildew continue to be posing serious health threats to those of us in humid environments. Bioterrorism is a concern, and of course, more recently, the global pandemic caused by the COVID-19 coronavirus has come to the forefront. Suffice it to say that the current generation of antimicrobial products do not meet the demand for more effective, sustainable, and longer-lasting protection compared to traditional cleaning products. So if we take a look at some of the products that are out there on the markets, I show 4 examples here that are either current or previously generated products. All of these have been very well disseminated in the consumer market space, but some of them have disadvantages, and some disadvantages of existing products, such as traditional disinfectants, is that they do not prevent recontamination of surfaces. They're often effective only against one class of a pathogen. They leach into the environment or they're consumed, leading to the loss of the antimicrobial activity. They lead to drug resistance. And again, the environmentally hazardous agents that are being used is what's really driving the need for new environmentally friendly antimicrobial materials because of increased regulation. Our solution is photodynamic coatings. Photodynamic coatings that are based on formulations that produce what we call biocidal singlet oxygen upon exposure to visible light. So we're focused on visible light, room light, what's typical output from LED bulbs, fluorescent bulbs, or even the sun, but not UV exposure. We're focused again on visible light. We're able to achieve a greater than 99.99% microbicidal efficacy that's effective against bacteria, viruses, and fungi simultaneously. That efficacy lasts for up to 30 days, which surpasses our voice of customer research requirement of 7 days. There's no resistance that has ever been documented against singlet oxygen because this is a non-specific oxidant. However, as a non-specific oxidant that is only survivable for about a few milliseconds, meaning it doesn't leach off the surface of a material, it's essentially harmless and non-toxic to both the environment and to a user. And so our overall viewpoint is that photodynamic inactivation, the illumination of a photodynamic coating on a fiber, on a surface, will be able to inactivate a wide range of pathogens responsible for the transmission of diseases. Now, photodynamic therapy is not new. It's actually a US Food and Drug FDA approved treatment for various different skin cancers, age-related macular degeneration, and other skin conditions such as acne and psoriasis. It's currently under the FDA review for the treatment of bacterial infections. However, we're using it as an alternative method for preventing bacterial infections. How does photodynamic inactivation work? Photodynamic inactivation has 3 key components to the mechanism of its antimicrobial action: visible light, a photosensitizer, and molecular oxygen. Visible light in that the photosensitizer, which is just a fancy name for a compound that absorbs visible light, gets excited into a higher energy state, transferring that energy over to molecular oxygen that's in the air, and that molecular oxygen gets activated to a reactive oxygen species or singlet oxygen. So singlet oxygen as an active biocidal form of molecular oxygen, hydroxyl radicals, superoxide, or peroxide. These different reactive oxygen species are capable of causing wholesale oxidative damage against pathogens, leading to their inactivation. Singlet oxygen is a powerful diffusible bleaching agent, so it's able to cause unspecific damage for which there is no resistance mechanism. That's going to be equally effective against drug susceptible and drug resistant bacteria, yeast, and viruses simultaneously. However, because it has a short half-life, it is harmless to the environment and to the user. Here you can see in these images some examples of how photodynamic inactivation works through pathogen oxidative damage. Here, prior to shining visible light on our photodynamic coatings, the Staph aureus and E. coli, as examples of gram-positive and gram-negative bacteria respectively, appear to have normal, healthy cell morphologies. However, after the photodynamic process occurs, where light is used with our photosensitizers on these fibers to create reactive oxygen species, those reactive oxygen species, such as singlet oxygen, give rise to the oxidative damage that you're seeing here, and the bacteria exhibit damage consistent with the leakage of intercellular components, leading to their inactivation. They're unable to proliferate, unable to be transmitted or infect new hosts. So again, extensive oxidative damage leads to bacterial inactivation. So what's an example of one of our coatings that we've developed? Here we have a very simple bicomponent mixture of a photodynamic agent that we can synthesize in the lab, but it's also commercially available, that we can combine with a photocross-linkable polymer, SBQ-PVA, as a bicomponent spray formulation. This bicomponent spray formulation, as an example, we can spray it onto nylon PA6 nanofibers that were provided from the NC State Nonwovens Institute. These nanofibers, instead of polypropylene, could be used as a nylon-based version of N95 mask material. But we've also sprayed this bicomponent mixture on other substrates such as wood, petri dishes, plastics, and glass. This bicomponent mixture, in the presence of UV light, causes a curing photocross-linking of the SBQ-PVA, essentially encapsulating our photosensitizer in a web-like structure that you can see here from the SEM images. We can do this either by dip coating processes or by spray coating processes, encapsulating our photodynamic agent within the photocross-linked SBQ-PVA. Now we can go ahead and take these materials and assess their antimicrobial activity, and that's what's shown here on these slides. I'll point out that the percent survival of the pathogens are noted here in a logarithmic scale. If we focus in on the left-hand panel, MISA is methicillin susceptible Staphylococcus aureus. ERIC is antibiotic resistant E. coli. In both cases, we see a photodynamic inactivation by our coating that's been sprayed onto these fibers by anywhere from 99.9% to essentially 100%, reaching our minimum detection limit. Again, illumination with just visible light. Those were antibacterial studies. In terms of antiviral studies, if we take a look at a common cold human coronavirus, not the one that causes COVID-19 disease, but a surrogate that is approved for use in biosafety level 2 facilities that we have available to us. You can see that in the absence of our photodynamic agent, we have 100% survival or infectivity of the human coronavirus. However, in the presence of the fibers that have been coated with our photodynamic agent, we're able to obtain anywhere from 99 to 100% inactivation of human coronavirus with just visible light illumination. Again, that can happen with either the spray-coated or the dip-coated materials. As a further example of our technology, we've been able to confer antimicrobial properties to medical textiles using, again, this bicomponent mixture of a photodynamic agent with a UV photocross-linkable polymer. You can see that on the left-hand side, we have a variety of different medical textiles provided to us by Vestcom America. And you can see in the photographic images prior to our coating process and then after coating with our photodynamic materials, we're able to see in the SEM images the effect of the coating on the fiber morphologies as well. Using these images with a whole other host of characterization methods, we've been able to determine that our coating thicknesses are roughly 1 micron. Because we're just coating the surface of the fibers, we have a very economical use of our photodynamic agent, about 10 to 100-fold improvement in the level of the photosensitizer present in terms of cost savings. And so this enables us to translate what is usually the most costly part of a photodynamic material, the photosensitizer, to being scalable for manufacturing processes, because now we've hit the cost savings needed for deploying these products and these coatings into the marketplace. As an example, against Staphylococcus aureus, a gram-positive pathogen, we're able to, depending on the material, obtain anywhere from 97 to 99.999% inactivation of the pathogen. Against human coronavirus, strain 229E, again, a common cold coronavirus that's very similar to COVID-19 coronavirus, we're able to achieve 90 to, again, 99.999% inactivation of human coronavirus. These were studies at the top panel were done using this porphyrin-based photodynamic agent. However, we can use commercially available photodynamic agents that are scalable at the needs that are necessary for deployment in hospitals or other consumer marketplace products. So we can use methylene blue or rose bengal, as we published earlier this past year. And again, we have excellent, very good to excellent photodynamic inactivation of gram-positive Staphylococcus aureus, regardless of the photosensitizer used. Excellent antiviral inactivation of human coronavirus, again, regardless of the photosensitizer that's used. Good to excellent inactivation of feline calicivirus, which is an example of norovirus or a surrogate of norovirus. And also modest to excellent antiviral activity against human adenovirus. So here we have an example of a gram-positive pathogen and 3 viruses, an enveloped virus in human coronavirus, a small non-enveloped virus in feline calicivirus, and a large non-enveloped virus against adenovirus. We don't have to just use this as a spray coating. We can actually take an olefinic block copolymer like Infuse 9107 and do a solvent cast and melt pressing technique to incorporate our photodynamic agent. And so photodynamic materials, our approach of using these photosensitizers is amenable to creating products that are in multiple form factors, whether that's coatings on surfaces, coatings on fibers, incorporated directly into fibers or directly into films, and it's compatible with practically any photosensitizer. And here you can see in the middle panel our olefinic block copolymer that contains our photodynamic agent that through thermogravimetric analysis shows that we have stability up to 300 degrees Celsius, which is amenable for use in hospital environments. The material turns out to be highly antimicrobial against gram-negative pathogens, shown here on the left-hand panel. We have inactivation ranging from 99.9 to 99.96% against these gram-negative pathogens, 2 of which are drug-resistant strains. Against the middle panel pathogens, which are gram-positive pathogens, essentially 100% inactivation to our minimum detection limit, including drug-susceptible and drug-resistant strains. And against vesicular stomatitis virus and human adenovirus, again, excellent, good to excellent antiviral activity. So again, highlighting the fact that we have broad-based antibacterial and antiviral activity in our photodynamic processes. And because these photodynamic materials, whether they're in the film form, fiber form, or coating form, are universally capable of inactivating pathogens, we believe that this is really a platform technology that's applicable to a wide variety of different consumer products in different marketplaces. While we are aiming for our beachhead markets being hospitals, healthcare facilities, and PPE manufacturers primarily, we have the ability to pivot towards other areas in the future. Really why we like these beachhead markets is because we understand very nicely the drivers of the purchasing decisions, primarily that hospital-acquired infections have a tremendous cost per patient, and that hospitals are really using means that are insufficient for combating these types of infections or surface transmission infections currently, and are really looking towards new technologies, disruptive technologies, such as the ones that we're developing. Tapes and films that can go on high-touch surfaces, that can cover high-touch surfaces in the medical space, or sprays that can be integrated into PPE production, either on clothing, masks, gloves, so on and so forth. So to summarize, I talked a little bit about our melt pressing, but primarily about our spray and dip coating applications. These are all scalable and translatable to manufacturing. We can create these antimicrobial photodynamic materials through a wide variety of high throughput methods, whether that's having these materials embedded or coated into polyacrylonitrile, nylon, block copolymers, coated onto textiles or upholstery. They all demonstrate very good to excellent antibacterial activity against drug susceptible and drug resistant bacteria, and also excellent activity against a number of different viruses that are either surrogates for or specific viruses that are known to cause infections in humans. Again, this is scalable, facile, and easily translatable to manufacturing. With that, what I'd like to say is that we are honored to be selected as a finalist for the 2021 IChemE Global Awards competition. Our contact information is shown here. You can contact us at NC State University or through Photosite Protection. Visit us online at photositeprotection.com. And once again, thank you for your attention, and I'm happy to be taking any questions. Thank you.
Okay, thank you very much. So once again, for the final time today, we'll pause for questions. So if you would like to get in touch, please do so now through the questions box. And if you've been suitably inspired by today's presentations, it might be time to start thinking about your own awards entry for next year. Keep an eye on the IChemE website for more details, but we plan to open for entries in early March 2022. Okay, there are no questions, so we're going to move on. Thank you very much, Reza. It's the moment that we've all been waiting for. It's time to find out who the winner of the IChemE Research Project Award, sponsored by the chemical engineer, is. Before we do that, I'd like to thank all our finalists for joining us today and for taking the time to share more details about their work. So let's start by announcing our highly commended entries, and they are the joint entry from North Carolina State University and Photosite Protection and Johnson Matthey. So well done to everyone associated with those projects. But now to announce the award winner. Ladies and gentlemen, the winner of the IChemE Research Project Award, sponsored by the chemical engineer, is the joint entry from the Abu Dhabi National Oil Company and MicroSilicon. So congratulations to everybody who worked on our winning entry. Dalia, I hope you're still with us. If you are, how does it feel to be an IChemE Award winner?
Hi there, this is so exciting. We were just chatting to the my other my colleagues, and we're all super excited. Thank you for the opportunity. It was excellent projects that were being presented, and we're just honored to be here, and this makes us extremely happy. Thank you very much.
Well, thank you, and congratulations to everybody who has worked on the winning project, and thank you everybody for joining us for the presentations, particularly our finalists, and for sharing more information about your projects. That is all for today. We've still got plenty more IChemE Awards webinars to come next week. We'll be back on Tuesday with 2 more awards webinars. But for now, thank you for joining us and have a great weekend.